Okay.
So I'll start then.
Yes, please.
This will be my fifth lecture. And so first of all, let me comment on the question yesterday. Yesterday's question was, there are two functors from Lie algebras to Leibniz algebras over K, and from Leibniz algebras to Lie algebras. So the functor G takes a Lie algebra and sends it to itself, viewed as a Leibniz algebra. And the functor F takes a Leibniz algebra and takes its canonically associated Lie algebra, which is H divided by 5 of H. And actually, these are adjoint. Actually, F is the left adjoint of G. G is kind of the inclusion functor, if you want to, inclusion of the category of Lie algebras into Leibniz algebras, and F is the left adjoint. Yeah, and this is, let's say, exercise. Yeah, but let me see what you have to show. You have to show that H G of G should be on Lie H Lie of G, yeah, F H, and this must be a bijection which is functorial. Yeah, I will not talk about the functorial nature of this bijection, but this is rather clear. And then, this bijection is true for one given Leibniz algebra and Lie algebra G, because every time you have a morphism of Leibniz algebras with values in a Lie algebra, the Leibniz ideal will be in the kernel. Yeah, so here the Leibniz ideal is in the kernel, and so it factorizes to a map from H Lie to G. Yeah, and in the other direction, you have to take a homomorphism of Lie algebras from H Lie to G and extend it by 0 to all of H. This is well defined, yeah, because the ideal is sent to 0. Okay, this is common to the question yesterday. And now let us take up the proof of the theorem. So remember, H, semi-simple, finite, dimensional Leibniz algebra over K of characteristic 0. And M finite dimensional H bimodule, then L P of H n is 0 for all p greater to 2, and there is an exact sequence. 0 goes to M0, goes to HL1, HL0 of HM goes to M sim HD, goes to H n goes to HL1 Hn goes to 0. Yeah, and this completely describes all cohomology spaces. And proof we have already reduced yesterday to the case simple H bimodule by using composition series for these finite dimensional bimodules. Yeah. And now step 1 is M is symmetric. So it is symmetric and simple. It is either M is symmetric, simple, and non-trivial. Yeah. Then the invariants are 0. Yeah. Then MH is 0. Because MH is a sub-bimodule. And MH equal to M would mean trivial, and therefore preceding the theorem follows from the preceding theorem. Yeah. Now, or M is symmetric, simple, and trivial. M is equal to K. Yeah. So what happens for the case M equal to K? Then we, as before, we shift arguments. And so, this is H and for all but H, the invariants are 0. Yeah. Why is that so? Because the invariants, the right invariants are the 0 cohomology space. And we have just seen that this is the first cohomology space of H, which is K, but we have seen before that the HL1 with trivial values, yeah, is the co-boundary operator here is just dc of xy is minus c of xy. Yeah, no action term because the action terms are 0. Yeah, and so this is exactly the same as the first cohomology space of the Lie algebra. Yeah, because the this is what we have seen. And so as HV is semi-simple, this is just 0, because the semi-simple Lie algebra is perfect. Meaning equal to its commutative support. So this is 0, and therefore, therefore these spaces here are 0. By the preceding theorem, these spaces 0, but for n greater or equal to 1. Oh. So you see here, if M is symmetric, all cohomology vanishes if it's a non-trivial module for degree p greater or equal to 0, but for non-trivial module only for degree greater or equal to 1. This is the first thing. And then the second step is M antisymmetric. And then we have seen by the lemma that HLN is minus 1 of H on H and symmetric. So you can convert this into cohomology with values in a symmetric module. And this 0 by the first step for n minus 1 greater or equal to 1. Meaning n greater or equal to 2. So this is where the second degree shift comes in. The first degree shift comes in from the trivial, from the possible cohomology of the trivial module, and the second degree shift comes in from the cohomology of the antisymmetric modules, where you have to shift first one argument in order to have a symmetric module. And so this is what happens. So the at this step we can already tell that for a semi-simple Leibniz algebra over a field of characteristic 0, finite dimension, the cohomology with values in symmetric modules is 0 for all degrees greater or equal to 1. And for an antisymmetric module, the cohomology is 0 for all degrees greater or equal to 2. And then the third step is arbitrary bimodal. And arbitrary meaning I keep the hypothesis that it is finite dimension. So have an exact sequence. M0 and sim 0. Recall this is the submodule generated by the x dot m plus m dot x, or m and m H. We have shown that this is an antisymmetric sub-bimodule of M, yeah, and the quotient is then a symmetric bimodule, yeah. And so it induces long sequence cohomology. And from the first part of this long exact sequence, we get the exact sequence of the statement of the theorem. So the exact sequence goes like 0 goes to H. H0 H and sim. And sim. Then 2, 8, and 0, which is then already 0. Yeah, because so first of all, for p greater or equal to 2, we have yeah, h p h and 0, which is 0, goes to h p h m goes to h p h and sim, which is also 0. And by the exactness of the sequence, we conclude that this one is 0. Yeah, this is the first part of the theorem for arbitrary bimodule now. And then let us evaluate the items in the long exact sequence. Then we will find this exact sequence of the statement. So M0 is an anti-symmetric focus. M0 is an anti-symmetric bimodule, and we have seen that HL0 are the right invariants. Yeah, but for an anti-symmetric bimodule, the right operation is 0. So HL0 for an anti-symmetric module is just the module itself. So the sequence starts with M0. Now, this is HL0 HM. Here, this is a symmetric module. Yeah. So it is just invariance. Yeah. But the Leibniz ideal always acts trivially from the left, yeah, on any module. This is also something we have shown in the lectures. So as this is a symmetric module, it also acts trivially from the right. Yeah, and so it is. I can also restrict to the H-Lie invariance. It's the same. Yeah, it's a little bit smaller, but it's the same. And then I go into HL1 of H with values in the anti-symmetric module M0. But now, yeah, we have seen that the co-boundary operator for the trivial module is just this term. But for anti-symmetric module, we have also this term. Yeah, but then 0. This is, yeah, because the action from the right is 0. So this means in equivariance property, yeah, this is equivariance with respect to the action of x from the left. Yeah, and this is what is meant when I write H Hom index H. Yeah, these are the equivariant maps from H as a left H module, yeah, with values in M0. Okay, and then comes HL1, HM, and this one is already 0, because we have seen that for symmetric H module, H by module, the H1 is already 0. We have cohomology vanishing for all degrees greater or equal to 1. Of course, only for the anti-symmetric that we needed also degree 2. So it goes to 0. And this is the exact sequence of the statement. So maybe you have questions. No questions. Okay, then now let us talk first about some consequences. First consequence is semi-simple Leibniz algebras rigid, are algebraically rigid. You remember Makhlouf's talk? Yeah, there was geometrically rigid when a certain orbit was open in the variety of Leibniz algebra laws. But here we kind of have a stronger statement. We have that all the H2, HL2 of H, comma H is 0. HL2 H, for semi-simple Leibniz algebra H. And this is, this means that semi-simple Leibniz algebra cannot be non-trivially deformed. Yeah? No honest deformation. And we have seen yesterday in Renato Fehlberg Jr.'s talk that these cohomology spaces come in the classification of algebras. Yeah? He was talking about Symbol algebras, so the situation is a little bit different, but these cohomology spaces come in the classification, and so the result that semi-simple Leibniz algebras are rigid is kind of a relief for certain mathematicians who ask these questions. This question before. Yeah? So this is one of the consequences. Now another branch of consequences is X dimension of the category of prime modules over Leibniz algebra. And so I will always talk about finite dimensional prime modules. Yeah? So actually, so in order over, and I will, and the theorem is, and this is by my student Jean-Louis. And so if K is the field of characteristic 0, and H, the finite dimensional simple Now I take simple, I not take semi-simple, I take simple Leibniz algebra. Okay. Then the category L each of the finite dimensional H modules is of X dimension equal to 2. Yeah. So what does X dimension mean? X dimension means for X dimension 1, yeah, contribute short exact sequences of bimodules, yeah, and X dimension 2 is the splicing together of 2 short exact sequences of bimodules. So this gives non-trivial, yeah, not equivalent to the split sequence, short exact sequences with 4 terms. Yeah. Maybe I write this in a slightly informal manner. Informally, there are exact sequences that are non-split, non-equivalent to a split. Exact sequences. That's 4 terms. These are the longest. The longest non-equivalent to split possible exact sequences of finite dimension. Yeah, the first theorem in this direction is due to Loday and Pirashvili for the semi-simple V. Our theorem is the first X dimension computation for a non-Lie Leibniz algebra. Yeah? But actually, this is not, yeah, the proof is not very complicated because it is just an adaptation of Loday-Pirashvili's proof. Yeah? So all the credit is to them in some sense. But yeah, what happens is at a crucial step, yeah, they take Loday and Pirashvili take Ntolo-Pirashvili's theorem to show cohomology vanishing, and we replace this crucial step by our theorem with Jörg-Feldfuchs. Okay, so in order to go into some details, yeah. I now go into some details about the proof of this theorem and the looping algebra, yeah, for any Leibniz algebra H. There is an enveloping algebra UL of H, which is the quotient of the tensor algebra on 2 copies of H by some ideal J. Yeah, HL, HR, 2 copies of H. This is tensor algebra. Yeah, free associative algebra if you want to. And so this is some ideal. And so the ideal is generated by exactly the things you impose on a module in order to be an H pi module. Yeah. And so what I should have said before is elements H L are denoted Lx, and elements of HR are denoted R. And so J is generated by I get L X minus L X Y plus L Y. Yeah, this is left. L is like left. Yeah, left multiplication by the bracket is equal to first left multiplication by y, then left multiplication by x, minus left multiplication by x, then left multiplication by y. This is what we call L and N. Yeah. Now you also have y plus x, y x. This is L and L. And remember, now you could take MLL, but okay, Loday and Pirashvili takes the consequence which we already had also. Yeah. This is the fact that right multiplication by an element y on something which is x dot m plus m dot x is 0. And so Loday and Pirashvili. So first of all, by its construction, it is clear that this is the associative algebra, which transforms these weird Leibniz bimodules into honest left modules over this associative algebra. Yeah? So this converts the theory of modules, of bimodules of a Leibniz algebra, into simply modules over some associative. And Loday and Pirashvili show in their paper that in this sense, Leibniz Sohomology is an X functor. Yeah, it is X P of the algebra UL of H of UH A with values in M. And this is the usual universal enveloping algebra of the Lie algebra H3, yeah, viewed as an anti-symmetric. Yeah. And so now you have two morphisms of associative algebras, D0 and D1, from UL of H to U of HD. One is related to the symmetric, to the anti-symmetric bimodules. Yeah, this is D0 is related to antisymmetric bimodules because they are 0 on the right multiplications, and D1 is related to symmetric. And so you can say now in fancy terms that when you give yourself an H of Lie module, left H of Lie module, then you can view it as a H bimodule via D0. Yeah? And if you look at it via D0, you get what we called before an antisymmetric H bimodule. Yeah? And again, you give yourself an H Lie module M, you look at it as a L of H module, meaning an H bimodule, via D1, yeah, and you get what we called before the symmetric H bimodule. Yeah, and so L of H category of finite dimension H bimodules. And so just to give you an impression of what we did in the computation and what Loday and Pirashvili did in their computation, I want to talk about the main tool of the proof of the theorem. These are the change of rings, spectral sequences, associated to D0 and D1. Yeah, and this is a very old tool. Yeah, this goes back to the book of Chevalley-Eilenberg on homological algebra. Yeah, dates from 1953, if I'm not mistaken, or 1950s, I should say. Yeah, so it is a very old tool. Yeah, and this tool just means to any morphism of associative algebras, you have an associated spectral sequence, yeah, which is called the change of rings spectral sequence. Yeah, and this is what Loday and Pirashvili write out explicitly for these two morphisms. And then get spectral sequences. One of them is PQ, P of U and HG. H. Y, A, X, yeah, and here Y is H Lie left module, and X and H on. So what happens here? Yeah, you take the X functor, yeah, in the category of UL of H modules. Yeah? This is an associative algebra, so you have the usual theory of X in this category. You take as arguments UH Lie seen as an antisymmetric UL L of H module, and some other bimodule. Yeah. You compute the X. This gives you not only an abelian group, yeah, and a K vector space, but also it gives you in fact an UH of Lie left module. Yeah? And so then take the X of left H Lie module, so if this Y with that one, this is the E2 term, and the spectral sequence converges then to the X, yeah? The X between this anti-symmetric, yeah? Anti-symmetric H bimodule, yeah, because at the base it is only H left module, and this arbitrary H bimodule. Okay, let's have only one of the spectral sequences, yeah, in order not to make it too complicated. But what I want to say is now, look, this one is exactly that one. Yeah, so this here is simply HLQ of H comma X. Yeah. So what I'm saying is, when you know very well the cohomology, yeah, of H with values in X, yeah, you can control the E2 term, and controlling the E2 term, you can maybe control also the X. Yeah, and so this is the method of proof. Yeah, because our theorem shows that for H semisimple, yeah, HLQ H X is 0 for all Q greater or equal to 2. Yeah. So there is not much cohomology left, yeah? And there are not so much rows left on the second page of the spectral sequence. Yeah? And so using the explicit description of HL1 and HL0, yeah, you can figure out, you can show that these spectral sequences collapse, and then you can figure out the X. Yeah, this is how one finds the theorem. Okay, maybe this can be enough for on these question of the categories of bimodules. Yeah, it permitted me to draw your attention on the fact that the Leibniz cohomology I wanted to talk about is an X functor, which is a very important remark. And now we still have 15 minutes. Let me talk about other consequences. Yeah, further remarks. So further remarks are, on the one hand, that yeah, can try to yeah, the Nicolo and Feldfuss W theorem is somehow an adaptation of Leibniz theorem to the Leibniz set. how about adaptation of theorems to theorems? Yeah. Actually, Dixme has a very early paper on the. I didn't quote it in my reference. Has a theorem about the cohomology of nilpotent Lie algebras. Yeah, and he shows two things in his paper. He shows that in case the trivial module is a submodule of the module in question, then there's lots of cohomology. Yeah, all the cohomology spaces are of dimension greater or equal to 2, except the zeros one and the one of dimension of the nilpotent Lie algebra. And on the other hand, if there's no, if the invariants are 0 of your module, then all cohomology vanishes. Yeah? And so one could try to adapt this theorem to the Leibniz context. Yeah? This is one of the things we are doing right now with Jörg. Another remark is Pirashvili's conjecture. And in order to make cut a long story short, I will not talk about the weak version of it and the strong version of it. Let's just say the weak version is that over C, let G be finite dimensional Lie algebra over C, and suppose HL dot G K is isomorphic to K. Yeah, I mean that the cohomology vanishes in all degrees greater or equal to 1, and in degree 0 it just is K, the ground field. K is C. Does this imply that G is semisimple? So, in fact, one can deduce from this cohomology vanishing that G must be a perfect Lie algebra and that the center of G must be 0. Yeah? But there are Lie algebras which actually can be used. Let me write this. Can be used from that G is perfect, center of G is 0, and H G is 0. Actually, maybe is that true? I think it's true. But this is not enough. Yeah? Yeah, Lie algebras. There are non-semisimple Lie algebras. Satisfy 1 to 2. They are called sympathetic. Said Benayani has worked on those, and there are still many open questions about sympathetic algebras. Yeah? Okay, this is one other bunch of open questions, but you can also have a higher point of view. Yeah. So what about the cohomology suggests that the operands of Leibniz algebras and associative algebras are similar in some sense. Yeah, because they both have this property that when you take algebras over them and you take the natural cohomology theory associated to it, then if for some algebra all cohomology H1 with values in all modules is 0, yeah, then all the HP are 0 for all integers P. This is the property we discussed. This comes from the swapping of an argument from yeah. And so this works for Leibniz algebra and for associative algebras. Can you capture this property, yeah, as an operatic property? Yeah? Can you characterize all operands which have this property? Yeah. So in which and another problem in the operatic setting is to say, can you define in general what a semisimple O algebra or some maybe quadratic or not. So you have, there can be very deep questions associated to these problems, yeah, because this is not easy to define. Yeah, here we only try to characterize these things in terms of cohomology theory. Okay, now maybe I should stop here. I still have a computation we could do together, but this is kind of an exercise. So I'm just talking about it very briefly. Here we talked a lot about the cohomology of semisimple Leibniz algebras. Yeah, I already talked about Dijkstra theorem and so the possibility to go to nilpotent Leibniz algebras. This is kind of the next simple class to consider. And so you can start with cohomology computations. And for example, the easiest nilpotent Leibniz algebra is the trivial Leibniz algebra on one generator. It is also the algebra. And you can compute the cohomology with values in the trivial module, and you find that the cohomology spaces are all one-dimensional in all dimensions, yeah, up to infinity. And now then you can take the second easiest the second easiest Leibniz algebra, maybe one which is not a Lie algebra. You can take this Leibniz algebra, and yeah, I defined to you before with two generators with F bracket F being E. And actually, the cohomology has been computed by another student of Jean-Louis Loday, and he showed that the cohomology spaces are also one-dimensional in each degree up to infinity. Yeah, so maybe this is a pattern. Yeah? Maybe Leibniz cohomology of nilpotent Lie algebras, that is in the trivial module, give always infinite dimensional cohomology. So maybe I stop on this question. Thank you for your attention.
Thank you very much for this nice course. I can see there is a question actually by Phanomezana Naravanyanaha. Please ask your question. So there was a raised hand there, so I don't know if that's not up to date anymore.
Yes, I am here.
Okay.
So I have two questions. So far we saw the cohomology of Chevalley-Eilenberg for Leibniz, the algebra, and Leibniz algebra, sorry. So I am wondering if there is other interesting type of cohomology for Leibniz and the algebra as well. And the second question is there a big difference between the theory of left and right Leibniz algebra?
Maybe I don't understand very well your first question. At least there's no cohomology I know about other than Chevalley-Eilenberg and Leibniz for Lie algebras. But these are kind of the correct cohomology theories from an operatic point of view. Yeah, you can every time when you have algebras over an operad, you have a general procedure to define operatic cohomology, and this may be one of the cohomology theories you're considering, but this coincides for the operad Lie with Chevalley-Eilenberg cohomology, shifted by a degree, by 1 degree, and for the operad Leib with this Leibniz cohomology, also shifted by a degree. Yes, and your second question was about left and right Leibniz algebras. These are, how to say, these are equivalent categories. Yeah, even I think isomorphic categories. Yeah, so they are very close, left and right Leibniz algebras. Yeah, so you can transform all the results from right to left and from left to right. This is not a problem.
Okay, thank you very much.
Any other questions or comments? Okay.
Thank you. Thank you.
Yes.
I see the Pirashvili conjecture said that G infinite dimensional Lie algebra. So is there any variant of this conjecture in the infinite dimensional Lie algebra?
Not to my knowledge. Yeah, so Pirashvili's conjectures, actually I wrote on the blackboard only the weak one, and there's a stronger one, which only supposes cohomology vanishing after some degree and not necessarily over C and so on. But all these conjectures are about finite dimensional Lie algebras. Yeah, I think in infinite dimensions it is much too too wild. Yeah, the problem is too wild to be answered. But it certainly makes sense to consider.
Mhm. Okay, okay. And I profit this question to say you, Professor Wagemann, a great thank for from Madagascar to this good talk, and we have a feeling that you are in our room as you write on the blackboard. So,
oh, thank you very much.
Thank you.
Yeah, it was a great pleasure for me too, and you are very welcome. And I'm very pleased to answer all questions you have maybe later. Yeah, if you think about these subjects and in 2 weeks or 2 months you have a question, then just send me an email. I'll be happy to talk to you about these questions.
Okay, thank you very much.
You're welcome.
And let's thank the speaker again.